Hi everyone, it's me, Carolyn. And today's video is going to be about discrete probability distributions. What that means is we will be looking at discrete situations. Reminder, discrete is when we have the outcomes of an experiment or something are just dots on our number line. And then eventually I'll turn to it in a different video. We'll talk about the binomial distribution, which is a specific type of discrete probability distribution. So what we mean is when we say probability distribution is we're going to be looking for the probability of all of those outcomes happening. So first of all, a little bit of terminology, and then we'll jump right into some examples and more things that go along with this idea. So first of all, a random variable is a numeric variable that depends on the outcomes of chance. They can be discrete or continuous. In this section, we're just going to look at the ones that are discrete. So again, remembering on a number line, just like dots along that number line somewhere. The probability distribution is basically what is the probability of each one of those things happening. In other stats courses, you would have taken a section that deals a lot with different types of probabilities. In this course, we only look at really simple situations as far as probabilities go. So the first thing we're going to do is create what we call a probability distribution table. And that table looks something like this. And what we're going to do is list all of the different values that our situation can take on and what the probability is for each of those values. So in this problem, we are going to roll a six-sided die. So the numbers, when we roll this die, first thing we want to do is list what our outcomes are going to be. So if I roll a die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. Those values will go in to our table as the X values. The probability of getting each one, well, if you roll a six-sided die and it is a fair die, the probability of each of those will be 1/6. This can be graphed if you'd like to. Different textbooks graph it differently. So what we would have down here is, again, we're going to be rolling a die. So this would be the outcomes of rolling a die. So we could have a 1, a 2, a 3, a 4, a 5, and a 6. And along this side, we would have our probabilities. I'm just going to abbreviate that. We'd also, of course, all graphs should have a good title, which of course should be better than my good title. And this is where the different textbooks will be different. Some textbooks will, like all of ours are going to go up to a height of 1/6. Some textbooks will just put a dot with a line for each of those. So we'd have like little dots. Others will make bars for each of those values. So depending on which text, whoops, I'm going downhill. Sorry about that. Depending on which textbook you're looking at, you will see different graphs. Very simple to make, usually done by hand. You could make a bar graph if you wanted to, or but in here I don't have my class that's taking this class. We won't be doing any of those, but you will be looking at them. So just be aware that they are available to see. If you want to look at this one, we can talk about it. It is a uniform. Because again, bring up some terminology from previous. Uniform because it is nice and flat and even. So there's an example of our first probability distribution. And we're going to do some more. So here we're going to flip 2 coins and we're going to let X be the number of heads that you get. So when we flip two coins, we could get no heads, we could get one head, or we could get two heads. Now, finding the probabilities, since there are three outcomes, it is not 1/3. So sometimes you need to write all of the outcomes down. So we could have had a tail and a tail. So tail on the first one, tail on the second, or tail on the dime, tail on the nickel, or tail on the left quarter, tail on the right quarter. We could have a heads and a tail. We could have had a tail and a heads, or we could have had a heads and a heads. So you'll notice that two of those outcomes resulted with one head. So our probabilities are going to be 1 out of the 4, 2 out of the 4, which we could reduce to 1/2, and 1 out of the 4. Yes, you could do these in decimal form as well. I prefer fractions when we're doing this simply because, in these situations, because I can then see where those pieces came from. If I had 0.25 and 0.5, someone would be, where did you get those numbers from? But I think seeing 1 out of 4, 2 out of 4, and 1 out of 4, a little bit easier to understand. All right, we're gonna do another one. We're gonna roll 2 die and let X be the sum. So we're rolling our 2 die, like playing a lot of board games. You roll 2 dice and you add them together. To do this, I'm first going to write my sample space. I left myself some room here because you could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. You could have gotten a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, and I'm not going to read them all off. Some people think that the 1 and the 2 and the 2 and the 1 are the same thing, but they're not, because you have two different dice. So it's like getting the 1 on one and 2 on the other versus the other way around. So just be aware that you can get them in different orders. So I'm taking a few minutes to write all of my sample space out. Hopefully it doesn't take me a few minutes, but more like a few seconds. Just so that we can see them all. Whoops, 5, 4. I like to do it in a pattern of some sort so that they're not all over the place, that there is some sort of organization to them. And what we can see is then our sum, the smallest sum we can get is a 2. And the largest sum we get is 12. But I think we can get everything in between. So the sum is what my X is. So this is kind of what we're looking for. What does our problem ask for? The sum of those dice. And now notice I did have an extra space just because I wanted to make sure if I didn't have enough room or not. I wanted to make sure there was enough room. So having extra spaces is just is fine. So the probability we can get a 2 is just getting this 1 and 1, and there are 36 possibilities. So probability of getting a 2 is 1 out of 36. Probability of getting a 3, well, then my 3 is here and here, so that's 2 out of 36, which I could reduce. I'm not going to in this video, but you could reduce them. Getting a sum of 4 is 3. You'll see that those sums are down the diagonals or along those diagonals. So there's 4 out of 36, 5 out of 36. 7 is the longest one, which is 6 out of 36. And now we start coming back down. So 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. So there we have all of our probabilities and the outcomes when you roll the die and you add those two things together. So X is going to represent the sum of those that you get. There are some rules that kind of go along with these probabilities. First of all, any probability in here, so any of those P of X's, has to be somewhere between 0 and 1. If we had a 0, that means that that outcome would not happen. If we had a 1, that would mean that that outcome would immediately happen. That would be the only outcome. So getting probabilities have to be between 0 and 1. I say that because when we get to further down the road and we calculate probabilities, you have to kind of remember they're always between 0 and 1. So if you get a negative value, you made a mistake somewhere. If you got a value larger than 1, you made a mistake as well. Another thing to remember is if you added all of these things up. So if I added all these guys up, I'm going to get the whole possibility, or we're going to get that 1. Okay. And sometimes that comes in handy because maybe you are missing one piece, or you have all of the pieces, or you have one piece, but you're looking for all the rest. And we'll see examples of that as we progress through this course. So that does come in handy, and here's an example of when it can. So suppose here were my possible X values. I don't know what they represent, 2, 5, and 7. Those are maybe that's the amount you can win in a certain game. And the probability for getting a 2 would be 0.45. Probability of getting 3 is 0.3, but we don't know the probability of getting that 7. If this is our complete table, we know that these 3 things have to add to 1. So I can add these 2 together, which gives me 0.75. And then I can subtract that from 1. And this is the value that would be going in right there because all of our values have to add to 1. Okay. Here's some more examples. Sometimes we have stories. All right, so a university keeps track of a pass and fail rate for students who take 5 courses. So if you have 5 classes, history shows that 78% of these students will fail none of them. So in other words, pass all of them. 9% will fail 1, 6% will fail 2, 4% will fail 3, 2% fail 4, and 1% will fail all of those classes. We can create a probability distribution table for this. So we're letting X be the number of classes that a student fails. And the probability of X will be the piece that goes along with it. So we could fail 0, 1, 2, 3, 4, or 5. Now the probability that we fail none of them, we can use this historical information and write that as a probability. Probabilities, again, are between 0 and 1, so we will write that percentage in its decimal form. We had 9% who failed 1, 6% who failed 2, 4% who failed 3, 2% who failed 4, and 1% who failed all 5. Notice I put it in decimal form, and remembering that 2% is 0.02. All right, so now we're going to use this information to answer a few more questions. We're going to say, what is the probability that a student taking 5 courses is going to fail more than 3 courses? So if I wrote that in probability terms, it would be the probability that X, our random variable, which measures the number of failures, is greater than 3. So when I say greater than 3, that means we're looking at 4 or 5. So I can take these 2 values, and all I have to do is add those 2 pieces together. So the probability of failing more than 3 would be 0.03. What is the probability that a student will fail no more than 2? So no more than 2. So that would be the probability that X is less than or equal to 2. So there's the symbols that we can use, the notation we like to use. The probability, that's what the P stands for. X being our random variable for this situation. No more than would be 2 or less courses. No more than 2 courses. So here we're talking about the 0, the 1, and the 2. So 0.78 plus the 0.09 plus the 0.06. And then I can drag out my calculator. I didn't need the calculator on the other ones because I can add those other ones pretty quickly in my head. This one, there's a little bit of carrying to do, so I thought I'll just be safe and use my calculator. Part C, what is the probability that a student will pass? Notice we switched to passing at least 3. So passing at least 3 would mean passing 3, 4, or 5, which means they are going to fail 2, 1, or 0. So passing at least 3 means failing no more than 2, which is exactly what we had done before. Let that sink in a little bit. Okay. Our next piece of terminology there is disjoint. So disjoint is when you have things that, two events, situations that you're looking at that they're said to be disjoint if they have nothing in common. So in other words, completely separated. Are there any of these above pieces that were completely disjoint? And the answer to that is yes. Because this first question and the second question, they were asking about 2 completely different sets. So those 2 would have been disjoint. Now, B and C are exactly the same thing. So of course, these 2 things are not disjoint. When we set up our table, each one of those events is disjoint from the other. So the 5 is disjoint from the 3, which is disjoint from the 4, and so on and so forth. So just another term to kind of keep in mind. We can talk about cumulative distributions here as well. We looked at a cumulative relative frequency on the ogive when we were graphing. We can, and that term cumulative means to add up. So what we do is we call this cumulative distribution. We use a capital F for some reason. And it's going to be the long run proportion. So basically adding up as we go. So it's like finding the probability that X is less than or equal to some C value, C being the possibilities. So let's consider an example, and we'll just kind of jump right into one. A family is going to have 3 children. Okay, and X is going to be the number of boys that are possible. So we're having 3. So I'm going to write down all of my possibilities. And I'm going to kind of try to do it in a systematic way. I'm going to let B stand for boy and G stand for girl. So we could have had a boy, and a boy, a boy, a boy, and a girl. Could have a boy, a girl, and a boy. So this is kind of like their birth order. A boy, a girl, and a girl. I'm going to do a girl, a boy, and a boy. A girl, a boy, and then a girl. A girl, and then a boy. Or I could have had all 3 girls. So if X represents the number of boys that we had, you'll notice that we could have no boys, so 0. We could have had 1, we could have had 2, or we could have had 3. There's no way to get 4. A lot of times when we have probability distributions, there's also values that can't happen. So a lot of times we don't list them because we don't want to have a lot of zeros in our probability piece. So we have 8 outcomes. We're going to assume that any one of these is equally likely from the other. So this would be 1 out of our 8. 1 boy, 1, 2, 3. So 3 out of our 8. There was 1, 1, and 1. This was 3. This one has 2, 2, and 2. This was 0. So here's also 3. and here is also 1. Sometimes I will do a quick check just to make sure that those things do add up to 1, because again, all of the probabilities do add up to 1. Now, if we're going to get our cumulative, the x values are going to stay the same, so we aren't going to change those, just like we didn't change those scale on the bottom. And we're going to start with the 1/8. And then what I do is I just add on the next one. So the 3/8, so this turns into a 4/8. I'm going to add on another 3/8. So that gives me 7/8. And then I add on another 1/8 and I get 1. So this is how we get our cumulative piece. Let's do another example. So here's another example. X is going to be the number of red lights that a driver usually runs through in a year. Hopefully you guys are on the upper end, so running through none. Some of us do push those yellows a little bit. Some of us push those yellows a lot. Some of us are probably should have kept going and had a few more red lights that we've gone through, but we will not go there. So here we're just going to be calculating our cumulative. So again, we are adding up. So we're taking that first is at 0.87. Now we're going to add on that 0.10. We're going to add on that 0.02. And then we add on the 0.01. Notice the last spot in all of those is always a 1, because you are adding up your probabilities. And if you remember, when you add all of our probabilities up, you should get the number 1. Just for fun, I did kind of draw this graph again. So you kind of see here's the 0.87. Then right when we hit the 1, it jumped up, and then it jumped up, and it jumped up. Okay. We can do some calculations on these distributions. So finding the mean or the average, or what is the most, if we did this over and over and over and over again, what can we expect to happen? The formula for calculating the mean, oh, I'm guessing we're doing median first, sorry. We can calculate the median is to find that spot where we're at the 50%. So we're going to be looking for where do we hit that middle, that 50%. So what we do is we look at our cumulative probability. And it's kind of like if you remember, we looked at percentiles and we did the ogive, that cumulative piece. So if we were looking for the median is our middle. So remember our box plots, we found Q2. Q2 was the middle of our data. It's also our 50th percentile. So it's kind of the middle. So 50% are below you, 50% are above you. So the 50% is at 0.5 when we're doing a cumulative. So here we're going to find that first time that we are bigger than that 0.5. Because sometimes we won't hit 0.5 right at the right smack dab. We might jump over it, like we've seen in some of these other examples. So for example, our 3 children, I should have went just back to the 3 children. Our f of x, we had the 1/8. I put it in decimal form just to make it a little simpler. So that was 0.125. Then we added this up and we would get 0.5. Here we'd get 0.875, and here we would get the 1. So our median would be 1. Another kind of way to think of this kind of method is if I looked at it in my fraction form, bring that page back, and had families with the situation. So I'd have these people listed. So I'd have one person with a 0. So I'd have him stand first. Then I'd have 3 people with a 1, 3 people with a 2, and 3 people with a 3. And if I were trying to find that median, we'd be right smack dab between 1 and 2. So it's a little bit hard to talk about that. So I mean, very upper end of the 1 would be our median. So our 50% would be below us, at or below us. Right, let's do another one. Oh, I also did that. So here we go. So here we have, yeah, I did ask a question. Do you need to actually calculate the whole cumulative piece? But I've needed to keep going all the way to the end. And the answer to that is no, because if I'm looking for the median, I just need to stop as soon as I'm bigger than 50%. So we're going to kind of do that. Here's another situation. We have a single tomato plant, and it will produce anywhere from 0 to 8 tomatoes. This is a probability of the number of tomatoes that we do. And we're going to calculate the median. So I'm going to calculate underneath that cumulative piece. So cumulative meaning we're adding on. So I'm going to be adding on that 0.05 to get 0.07. We're adding on the 0.1. We're adding on the 0.1. We're adding on the 4.2. And now notice I'm larger than 50%, so I can stop. So my median would be 4. As soon as I get to a value that is bigger or equal to that 0.5. We can also calculate the mean, the average. And here is how we would do that. It's kind of like a weighted mean, where we have our X values. Those are the values that would be adding together. Their weights is the probabilities. So think about 100 people up here. If these are my weights, 42 of those people would have a 4 attached to their chest. 25 of those people would have a 5. And I'd be adding up all those values that I see and then dividing by that 100. So this is kind of like the weight, because I'd have 25 5s. I'd have 42 4s. So that's their weight. So to find the mean, or what we expect to happen, if we did this over and over and over again, we can take our add. So this again reminds us to add up our values multiplied by, so this is multiply the probabilities. Okay, and we're going to do a couple of examples. So here's that tomato problem that was on there. So we're going to find, on average, how many tomatoes should we get? Now, if I look at my data and just kind of look at those probabilities, first of all, I know the mean has to be somewhere between the different outcomes that I'm getting. And the outcomes I get are 0 and 8. So my mean is somewhere between 0 and 8. I also see that I have a lot of tomatoes in this 4 and 5 range. So they're going to kind of pull that mean towards them. So we probably will get a mean somewhere in the 3 to 6 range would be my guess. But we will actually calculate it. So we're going to take, again, we're going to add up our X values multiplied by our probabilities. So I'm going to take my 0 and I'm going to multiply it by that 0.02. Then I will add the 1, and I'll put this in parentheses instead of a multiplication dot. We will add. So I'm taking each value and I'm multiplying it by its corresponding probability. And I'm going to run out of room. Okay, now remembering that order of operations tells us we have to multiply before we add. So I'm going to multiply these values together. Hopefully I'm doing this multiplication correctly. I am going to drag out my calculator though to add them up. That's 0.07 and add a 0.08. And I have 3.92. So on average, we expect tomato plants to carry about 3.92 of them. So if I had 100 tomato plants, I'd get about 392 tomatoes complete total. So about 3.92 per plant times my 100 plants, I'd get roughly 392 tomatoes out of that. All right, we're going to do another one. We are going to flip a coin 3 times, okay? And we're going to count how many heads we get. So again, this is going to be similar to our 3 boys. So I'm going to write those out, except using heads and tails. So I could get that head, 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 my head, head, tail, my head, tail, head, and my head, tail, tail. I have done this sample space kind of thing for so many years. I have this memorized. And what I usually do is just start with my 3 heads, and then I'll flip the last one. Then I'll turn it back to the normal and flip the middle, and then I flip it. Then I flip the first one, and then basically repeat the other ones. So that's where how I get that so quickly. We could have 0, 1, 2, or 3 heads. So if I put how many heads next to each one, I had 1 out of the 8, 3 out of the 8, 3 out of the 8, and 1 out of the 8. Now, if I'm finding the median, we need to look for that f of x, and we look for as soon as I hit 0.5 or half. So I'm going to start with my 1/8. We're adding on the 3/8. So that gives me 4/8, which is 1/2. So I'm done. So my median is equal to 1. My mean, we need to take our values and multiply them by their corresponding probabilities. And I could do this in decimal form, or I can do this in fraction form, whichever you are more comfortable with. I will probably switch once I get them all multiplied together, because for me, it's easier to multiply fractions than it is to multiply decimals, because all I need to do is multiply the numerator. I suppose this isn't too hard to add up. 6 and 6 is 12. If I reduce that down, they're both divisible by 4. I get 3/2, which is 1.5. So on average, and we would think that that would be about right, because this is nice and symmetric, 1/8, 3/8, 3/8, 1/8. The middle is going to be, or the mean will be right smack dab in the middle there too. It makes a little bit of sense to get an average of 1.5 flips. Heads every time we flip it. Okay, I think we are just about done, because we can do this. So we're going to look at another example of what can we do also. Once we have that mean, can we use it for something else? So I chose M&M cookies, because why not? M&M cookies are yummy, yummy, yummy. So we have a cookie can have anywhere from 0 to 4 M&Ms. 4 would be my preference. I'd actually squeeze a few more in, but that is not the case when they're going down the convection line, I suppose. So first thing we're going to do is find the median, just for practice, and we'll also find the mean. So basically, if I picked one on average, how many would they have? So averaging them all up. Notice we don't have very many that have few. Most of them will have up this way. So I would guess that our average is going to be up towards the end. Average has to be somewhere between 0 and 4. Our median has to be somewhere between 0 and 4. To find the median, we use that cumulative piece. So we're going to add those pieces up. So I'm adding on. And I'm going to go until I hit 0.5, not 0.05, 0.5. Because we're looking for 50%. Well, it looks like I have to go all the way to the end because I didn't hit 0.5 until, or bigger, until I got to the 4. So the median is the number 4. And if you think about it, if we had 100 cookies and each of them had a number on them as to how many chocolate chips they had, and we put them in order, we'd have 75 that would have the number 4. And if we were looking for that middle cookie, we'd still be in our 4s. Okay, to find our average, we take our value and multiply it by its corresponding probability, and then we add all those up. So I'm writing my value x, multiplying it by my corresponding probability. So this is 0 plus 0.02 plus 0.04 plus 0.6 plus, I think that's a 3. I'll double check with my calculator here. It is. And now I'm going to add all those up. And I get 3.66 chips. So on average, each cookie has 3.66 chips on it. So we're going to consider a little bit further that the calorie count for an average M&M cookie is determined by the piece above. We are going to be finding the calorie count. So each cookie part of the cookie, so not the chips, but just the cookie part, the breadier part that keeps it together, has 50 calories. And then each M&M contains 10 calories. So we are going to calculate our calorie count per cookie. So I'm going to kind of write this down. Calories is calculated by taking our 50 calories per cookie and then adding on 3.6, no, that's not what it is. It's 10 calories per M&M, right? Okay, but each cookie has on average 3.66 M&Ms. So I'm going to put that into this piece here. So their calories would be that 50 plus our 10 times the 3.66. Or, remembering we multiply before we add. So each cookie would have roughly 86.6 calories. So that would be how we would do that. And you can do this with more complicated situations as well. Kind of like I did with the 100 tomato plants before. If we had 100 tomato plants, how many tomatoes would we get? Each tomato plant on average got 3.92. So we had 392 total tomatoes. I multiplied those together. I hope that this is starting to make a little bit more sense. With practice, which I hope you guys do, they will be even more. But I will see you in the next video. Our next video, we will look at a specific type of discrete distribution and look at the binomial. Have a wonderful day.